you very much for having me. So I'm very pleased to present this work. So this work has been published very recently in Nature Geoscience, and I'm really pleased to present it to you in more detail and having the background and stuff like that. So first, as you see on the first slide, there is many there are many partners for this study. So many co-authors. So just want to emphasize that it's a group effort. So we work for a bit of time with every members of this team, and everyone come up with ideas, and we develop these ideas in concept to come up with that paper, and it was a very thrilling experience, I can say, and I really want to thank Professor Lee, because without him I would not be in Curtin and not doing this great job actually. So that's just for an introduction. So today I will discuss about the deep connection between mantle dynamics and what we see on the surface, so like oceanic basalts and supercontinent cycles. Okay. So as background of the study, I will just start to explain why we did that study, okay? So basically, when you look at the Earth, actually, so present day Earth, you see there is, using the tomography and the seismic, you see there is two massive structures down below in the Earth. You know, they are called the large low shear velocity provinces, or LLSVPs. So on the right here, if you see my pointer, you see it's a tomographic image at 2,800 kilometers. And you see in the Pacific and below Africa, you have this LSVP, or as we call them, the super plumes, because they control, they mainly control convection structures and the formation of plumes on Earth. So we'll talk about that later. But if you see, you have these structures down below, and on the surface, we have the Pacific Ring of Fire, or what we call the subduction girdle. So it's divided the two mantle domain we see actually. So we have in blue here the Pacific domain, and in the yellowish, the African domain. And what's interesting is each mantle domain possesses an LLSVPs, okay? And this is what we want to understand, how we came up with that structures, that's today's structures. So exactly what I was saying, so we want to understand the nature and evolution of the LSVPs, or the super plumes, and the link with plate tectonics, and more in general with the supercontinent cycles. So all along with this talk, I would talk about the supercontinents and the supercontinent cycles. So just to make sure that we're talking about the same thing, we're on the same page. What are the supercontinents? So the supercontinent is when you have the majority of the land masses gathered together, packed up, representing more like 75% or something like that, you know. And we know we have several supercontinents through time. So on this time scale here, you see at 0, it's present day. We had Pangaea. Before that, we have Rodinia. Before that, we have Nuna, and maybe more supercontinent or supercratons before that. When we talk about the supercontinent cycles, we're talking about the link, you know, between the assembly, tenure, and dismiss of the supercontinents and the beginning of the next one. And usually, the supercontinent cycles is between 500 and 600 million years. That's what we call the supercontinent and supercontinent cycles, right? About the superplumes, as I said, the superplumes are the LLSVPs. So they are this massive structure in the mantle that control the formation of the major hotspots and large igneous provinces on Earth. So back to the image of the tomography at 2,800 kilometers, you see in the red dots here are the present day major hotspots on Earth. And you see they are all closely linked to the LSVPs, or the superplumes. And these regions are thermal anomalies, and as I said, they control formation of the supercontinent, control the formation of the hotspots and lips. I think I should have a very nice, animation here. So this is a representation of the LSVPs done by Kotar et al. In 2016. You see that we have the Pacific LSVPs passing by, and after that you have the African LSVPs. This animation is very nice because what you see is the two structures are antipodal. You know, they are not just somewhere in the mantle, they are basically at the opposite on the core, you see. And you see they have different shapes and stuff like that. So this is just a representation of what's going on deep in the mantle. So back to the link between the supercontinent superplumes. So start with the superplumes again. What we see today is we form the hotspot and large news provinces above the LSVP, or at the edge of the LSVP, to be precise. And this idea is not new. It's something we know for quite some time now. And on that paper by Burke et al. 2008, they reconstruct, using the paleogeography, they reconstruct the position of the large news provinces and hotspot when they were formed. And what you see on that map is most of the lip for the last 200 million years form at the edge of the LSVP for the African LSVP or the Pacific LSVPs. So based on this study, these authors said, okay, so for 200 million years, the lips and the hotspots are forming the same place. So basically the LSVP should be fixed. So they are there, they're not moving, and they're producing the hotspot at that place for at least 200 million years. And they postulate that it has been the case since their formation, probably from the beginning of the Earth. But this is in contradiction with geodynamic modeling. So in 2008, in this very important paper, Li and Zhong demonstrate that using geodynamic modeling, that the LSVP are not fixed. So if you look at the model here, so when we start with the Earth with is a degree N convection mode, so we have like multiple upwelling, multiple downwellings, and if you form supercontinents, so above here, above the downwelling, then you're gonna start from a degree 1, so with big downwelling here and an upwelling on the other side of the Earth. You're gonna form a subduction girdle all around the supercontinent, and the subduction girdle will have deep, profound effects on the structure inside of the Earth. You're going to have a formation of an upwelling below the supercontinent and formation of an antipodal upwelling on the other side. And this will control the position and the formation of the plumes and the SVPs. So we have a geodynamic modeling that predicts higher mantle temperature and higher mantle activity during supercontinental breakup, and close control of the LSVP location by supercontinental assembly, which suggests that the LSVP are dynamic, by contrast with what we think based on the reconstruction and the position of the lips. This idea of fixity between dynamic of the LSVP has been challenged for quite some time now. No, not quite some time, very recently, actually quite the opposite, very recently. For example, in this recent paper in Nature Com 2019, Bono et al. Showed that the hotspots are not fixed based on their model, their analysis of the Hawaii and Umpro chain. They demonstrate that the hotspot is moving, and more importantly, they demonstrate that the LSVP itself is moving about 30 millimeters per year. For example, they show that the African LSVP should be moving downward south, so basically moving. So this recent motion expressed by the hotspot may challenging directly the fixity of the LSVPs. And we were also very busy on our group to work on that subject. And we had 2 papers last year, one paper in Nature Communication and one paper in Geology. And what we did, so Hamed Gamal Eldian, which is a PhD in our group here, did an amazing job by collecting all the available data on basalts throughout time. And we did some bootstrapping modeling, and we did some statistical modeling. And we showed there is a correlation between the plume activities and the supercontinent cycles. Myself, in publishing Geology, we show that the oceanic largeness provinces for at least the last billion years are closely linked in terms of occurrence to the supercontinent cycles. We have published 2 papers that demonstrate the geological and geochemical record of the mantle plume. They suggest a strong relationship between supercontinent and superplumes. So once again, we are moving towards something that predicts a close relationship between the supercontinent cycles and the plume activities. Just to have a glimpse of what we did, this is the 2 main results from these 2 papers. So paper in Nature Communication, we show that the difference, so in this diagram, which is here is the age 0 from today to 3 billion years, we have the variation of chromium. So this is above the average. So when it's orange, it's above the average. When it's brown, it's below the average. And we saw we have excess in magnesium, nickel, and chromium, which are indicative of higher temperature during melting of the mantle to produce the basalts. We saw we have excess of these elements at the tenure of the supercontinents. So we have this tenure and breakup of these supercontinents. We have this relationship. And for geology, in blue, you have the oceanic plume record, so which are the oceanic plateaus and the OIB preserved in the ophiolites. And doing statistical analysis, we show that we have a 500 to 400 million year cycles to produce this oceanic plateaus, and which is coincide with the continental lips. So from now on, we have evidence, and we think we have a close relationship between supercontinent and superplumes. And this relationship, supercontinent and superplumes, predict a feedback between the Earth's mantle and the lithosphere. So we think there's a close connection between down below to the surface. That's what we think, and that's what our paper shows, and other papers. So the question is, if you have a feedback, the question is, if you have a feedback between the surface and the deep mantle, so it means like we should find signature in the mantle that could explain things, you know, that we should be able to see this connection between the supercontinent cycles, the assembly of the supercontinents, and what's going on in the mantle. And one of the best way to study the mantle, to have like to see the story, what's going on in the mantle, is to look at the isotopic composition of the mantle. And to do that, we are using radiogenic isotopes. And the direct way to study these isotopes is to look at the oceanic crust, because the oceanic crust is formed by direct melting of the mantle, and there is no interaction, no complication by the continents and stuff like that. And this idea is not new, and it starts really on in the history of geochemistry. If you look at one of the major papers started in 1983 by Dupré and Allègre, they show that there have deep mantle heterogeneity in the mantle using the lead isotopes, the strontium isotopes. They demonstrate that the mantle is heterogeneous and it's large-scale heterogeneity. And back then, they tried to understand why do we have this heterogeneity. Just after that, in 1984, Art produced this map here, when he analyzed, you know, the statistical distribution of these anomalies, and using different type of isotopes, like the different type of ratio, for 207 lead, for 204 lead, or 208 lead, etc., etc. They demonstrate. They demonstrate that you have generally the Earth has a big anomaly, what you call it, the Dupas anomaly. So the Dupas anomaly stands for Dupré and Allègre. So basically, how it works. So they show that compared to the northern hemisphere basalts from the MORBs and the OIB, the southern hemisphere basalts are usually enriched compared to that line here. Okay, so it defined the northern hemisphere reference line, which say like this is the normal mantle per se, and all the basalt below in the southern hemisphere, are enriched. And you call that the Dupas anomaly. And they try to explain these anomalies by what's going on in the history. So if you look at the northern hemisphere line here, you can interpret it that by ancient mantle as being something ancient happened in the mantle around 1 billion years ago, or something like that. And they say that this heterogeneity must lie something with the breakup of Gondwana. So already back in the day, they say, oh, something happening with the breakup of the continent, and something can modify deeply what's going on in the mantle. Right after that, people say, okay, we have large mantle heterogeneity in the mantle, and now we want to understand why, and we want to understand the extent of this heterogeneity. And already the same year, like 2 years after that, Art published this paper, Castillo presented a new refined model of the Dupas anomaly. So once again, in the southern hemisphere, you have the Dupas anomaly, and he demonstrated that within the Pacific, you have what we call the SOPITA, the South Pacific Isotopic Thermal Anomaly. So he come up with more complication with the story. So we have the triple anomaly, north-south, dichotomy, and then within the anomaly we have more complications. And he expressed that as an heterogeneity within the triple anomaly between what we see in the African, Atlantic, and Indian Ocean, and what we see in the Pacific. And since then, the story continued to be more and more complicated, with more data acquired on these islands, with more tomographic data acquired. People come up with new ideas and new way to map the mantle heterogeneity in the mantle. And it come up with very good paper, for example, by Jackson et al. In 2017, where they collect the composition for the major hotspots on Earth, and they show a direct link between the temperature of the hotspots and the helium composition, for example. So they try to understand what's going on and where are the primordial signature, where are the enriched signature in the mantle. Later on in 2018, they did pretty much the same work based on other isotopes, like the late isotopes, transition isotopes. And they again try to understand and map the heterogeneity in the mantle and try to link them with what's going on with the LLSVPs and all the superplumes. But as you see in these diagrams, it's very complicated, and there is no clear answer popping up. So it's like the signal is still a bit blurred. Then people also try to understand more in detail what's going on in the hotspot for individual hotspots. For example, this is a very important work in Hawaii, looking at mantle heterogeneity within the Hawaiian and Emperor chain plume. And what they saw in that paper by Weiss in 2011 is within the same hotspot, you can see different heterogeneity between different lines of volcanic activities. And they try to link that to what's going on deep inside and in the mantle. And they propose that the composition within the hotspot can be modified by where the material come from. Is it close to LSVP, or it's more from the ambient mantle? So as you see, this is something going on, and there were a lot of questions still to answer. And why do we have no clear answer yet? It's because we have a very blurred signal. So in that diagram, this is the compiled data for the OIB, and also including oceanic large genus provinces and MORBs from both the African domain and the Pacific domain. Just as a reminder, here you have the African domain, here you have the Pacific domain. So again, as a reminder, the OIB are believed to be deeper sourced from the mantle, so maybe more representative of the lower mantle, and the MORBs more representative of the shallow mantle. But in each case, for each domain, we see that the composition seems roughly the same. And this is why we don't have the clear view, because we are treating every hotspot or every ridge as equal in the way we treating data. But what we know for sure is that plume are not made equal. That's something, and that's an idea borrowed from Chris Spencer. So thank you, Chris, if you're hearing that. So yeah, the plume are not made equal. You know, it's not because we have an hotspot that they all hotspots form in the same way. And that has been summarized by Cotillo in 2003. So Cotillo et al. In 2003 make a framework in which you can study the hotspots, right? So this is a schematic view summarized by Copper et al. in 2011. When you have like the three main hotspots, the idea of the three main hotspot and the Middleton ridge as well. So basically, you have the hotspot that come directly from the core mantle boundary without interaction with anything. So just going up, producing the chain. You have the hotspot above the LSVPs, producing the large genus provinces and also maybe a hotspot chain. And you have hotspot that only form on the uppermost part of the upper mantle. And in that, you also have like the mid-ocean ridge, or just, just the shallow part of the upper mantle. So using that framework, you just realize that if you want to have an idea what's going on deep in the mantle, you need to filter the data. So basically, if you want to filter the data, you want to exclude the mobs, which are just representative of what's going on just below the surface. And you want also the hotspot like tip 3, which are also just below the surface per se. And you want to focus on the hotspot that we are deep sourced, okay, the deepest source. So what Coutinho did in 2003, he came up with a list of criteria based on the isotopic composition for helium, for example, the buoyancy, in the geological history. If you have lips in the beginning of the history of the plume, if you have hotspot strike, a lot of different criteria. So based on what people did in the past and based on Coutinho framework, what we did is say, okay, we're just gonna update this criteria, and we're just gonna reassess the composition of these different OIB or ocean island and lips to see what's going on. What is there a difference? So we just go back to we did our homework. So we go back for each hotspots. We did a geological history for each hotspots using the recent published tomography to see if there is a source, if the tomography can see the deep, the panache come from the surface to the core mantle boundary, this kind of stuff. And we try to include only hotspots with a clear deep origin. So we refilter the one with deep origin from the one with, I would say, ambiguous or more ambiguous, because everything is ambiguous. But let's say when we are sure we have deep origin, we just collect this one and we take it for sure, okay? And we produce this map. So on that map, this is the map of the LSVPs at 2,800 kilometers, and we have the major hotspots, today, present day hotspots. And you see for each domain, so here it's the African domain, here's the Pacific domain, we have 4 hotspots for African domain and 4 hotspots for the Pacific domain that can be characterized as deep sourced, so deep origin. From Iceland, La Réunion, Tristan, and Kerguelen for the African domain, Hawaii, Galapagos, Easter, Louisville, or Old Tongue Java for the African domain. But the story doesn't stop here, because what you have to do when you have these basalts is you need to understand if their composition relies on, if their composition, give you information or their deep source. And there is complication. And for example, Samoa is quite complicated, because if you look at Samoa, it should be included in the deep source hotspot, but Samoa have a big complication because it's a plume slab interaction. So it has been published and demonstrate that Samoa have interaction with the slabs and the plumes, and which end up with very complicated isotopic compositions. So Samoa is an exception case here, it being too enriched for a deep source basalts, but we have an explanation about it. So we have excluded Samoa, and this is a good example to say that we scrutinize every hotspot and every geochemical composition to make sure that is there pristine compositions. Do we need to exclude these guys or not? And this is produce every hotspot the rationale if they need to be included or excluded. So once we have this framework, we select the hotspot, we need to have the data, right? So what we did, so we go to the online database and we collect all the samples for which we have lead, strontium, and neodymium isotopes. And because we want to look at the primary mantle product, we select the basalts. So for the basalt, we have a very large, no, we have not a large, but we have a very restricted composition, okay, for the silica. So we just select the basalt. So the silica between 40 and 50%, and potassium and sodium generally lower than 10%, to be general. Also all the mafic products of the flumes. So we end up with more than 6,000 samples, and we filter them according to deep or non-deep source, and we end up with almost 2,600 samples for the deep OIB and around 3,000 for the non-deep OIB. Something I need to mention here, so in the filtering process, once we get the sample from Kerguelen, we see some complication in Kerguelen. So, for example, Kerguelen is characterized as deep source, but we know in its history, the large Indus province have an interaction with the continental rocks in the early history because Kerguelen plume is responsible for the breakup of Gondwana. And in a recent compilation by Olirock et al. In 2019, they demonstrate that all the rocks older than 95 million years are contaminated by the crust. So these guys has been excluded from our compilation because their composition did not reflect the plume, but reflect the interaction with the continental crust. And once again, we did that for every hotspot to make sure that we don't have like complication based on that. And this is the results of our filtering. So in this diagram, so two lead isotope diagram. So for the African domain here, the deep African OIB and the deep Pacific OIB, we see that the signature is quite different. And to emphasize this difference, we use a statistical characterization of the distribution of the isotopes. We use the kernel density estimate for all the isotopes, and this produce these lines here. So when you see here, so you have like the majority of the samples concentrate here for the African domain, for 206, 204, and 208, 204, and here for the Pacific domain. And we did that for the lead isotope, the strontium isotope, neodymium isotopes. And what we see here, we see that statistically, African domain and the Pacific domain, summarized here, they have different isotopic compositions. So just applying the filtering of the deep OIB and non-deep OIB, excluding the MOBs for now, we saw that we have a distinct geochemical composition for the two domains. And ending up with that, we say that's really interesting. That's really interesting results, because if you look at in detail, you see that the Pacific domain, sorry, has a very, I would say, mantle-like composition. It's something you can expect for the mantle. You know, mantle should be on that line and have no complications here. When you look at the African domain, you see like it's systematically enriched and systematically above the Northern Hemisphere reference line, okay? So it's look like the African domain experienced something that the Pacific domain didn't experience. And this is something we had to understand. So when you look at the composition, you have here the different M members. So EM1, EM2, the upper continental crust, the prima, which is the normal mantle. We see that in general, we have the African domain is a mix between the continental crust and the EM1, EM2 end members here, or even here. Okay. So what we did, you say, okay, so let's say what can cause this such similarity? So it should be a mix with this recycled stuff. Okay, so either sedimentary rocks from the ocean or from the continental crust. So we did a modeling. So it's a rather simple modeling. So basically what we modeled, so we modeled the evolution of the normal mantle of the prima through time from 200 and 500 million years to today. And we also modeled the composition of the upper crust, okay, from 250 million years to today. And what is interesting is if you look at the distribution here for the African domain, for the both isotope systems, you see that you end up in a space which can be modeled by interaction, a mixing between the prima, so the mantle, and the upper crust from 0 to 700 million years. So what we see here is the African domain can be explained by just a mixture between the continental crust component and the mantle. And it can be traced back to 700 million years. So the question was, what happened 700 million years ago? And actually, if you look at the history of the Earth and the paleogeography, 700 million years ago basically is the transition between Rodinia and the assembly of Pangaea from 700 million years ago until today. So we are covering the breakup of Rodinia, assembly of Pangaea, tenure of Pangaea, and breakup of Pangaea. So once we had this idea, we say, okay, we need to put that into context. We need to understand, you know, how it moves, how the mantle domain evolves through times. And for that, we use the framework established by Lee and co-author in 2019 on the superocean paper. What they show in that paper, they show that the supercontinent cycles is not just assembly dismissed of the supercontinent. So you have something that superimposes that, which is the supercontinent, the superocean cycles. If you start with Nuna, which is what we believe one of the first supercontinents, you have Nuna, and when Nuna starts to break up, the breakup was not complete. So you have the external ocean of Nuna stay the same, and we have the breakup of Nuna, which could be explained as incomplete or not incomplete would be fine. And then you assemble Rodinia pretty much in the same place. So the external ocean stay the same, okay? So from Nuna to Rodinia, you have the supercontinent, which is pretty much in the same place, breakup, assembly, and the superocean remain the same. On the other hand, what they demonstrate in their paper is that from Rodinia to Pangaea, you have what we call extroversion. So it means like when Rodinia break up, so I can try to make the relation here. So when you have the breakup, the breakup was very complete and Pangaea assemble on the other side, pretty much. And when you do that, you destroy the external ocean and you create a new ocean, and a new external ocean. And this is something I can express here. So this is, so if we start here from Rodinia here, this is an expression. So you have Rodinia here, you have the subduction girdle here. So you're gonna start to make the plume that will break up Rodinia, and you produce the antipodal superplume on the other side of the Earth, right? And this will trigger the breakup of Rodinia. And then you're gonna have here the superocean. This is the superocean of Rodinia, and the superocean of Rodinia will be destroyed when you assemble Pangaea on the other side of the Earth, and you're producing a new superocean here. Then you have Pangaea, which is assembled here, and you have the new superocean, which is the Panthalassa and Paleo-Pacific. And then you start to break up Pangaea again, but this is another story. So based on this evidence, we try to put that into context to see what's going on with the mantle domains. And this is a bit weird. So we start here, go in that direction, and go here. So here it's the Earth, reconstruction of the Earth 600 million years ago. You have the Mirovoy superocean, which is the superocean of Rodinia, which will be the future African domain, right? And we have here the internal ocean when you have the breakup of Rodinia, which will be the future Pacific domain. Then you continue to the breakup, which is complete, and then you consume the Pacific, the Mirovoy superocean, and you're producing the and you consume and you produce the Pacific domain here. Then you have Pangaea, which is assembled here above the African domain, so the ancient superocean of Rodinia, and you have the Pacific domain. And then you have the breakup, and you are in the present day configuration here. So this is the framework we established for that, and this is the two main conclusions of the paper. So we have the subduction polarity associated with the supercontinent cycle in superocean. Can best explain why the African mantle domain is contaminated with continental crust material, whereas the Pacific mantle domain has been protected from such contamination for the past 600 million years. And then the deep mantle geochemical dichotomy show that the two mantle domains may have been geodynamically and chemically coupled with the supercontinental cycle, suggesting dynamic instead of stationary nature of the mantle domain structure. Something, the take-home message would be when you have like the transition from Rodinia to Pangea, you have extroversion, and when you do the extroversion and the accretion, you form Gondwana and then you form Pangea. You have massive subductions and massive orogeny that will bring a lot of continental material within the mantle. And then you have the subduction girdle, which bring all the material that could be go up the continent back into the Pangean domain or the African domain. And because the polarity of the subduction, the Pacific domain is preserved from that process. This is why we have a distinct geochemical signature in both domains. Well, thank you.